Hey everybody, so let's talk about our final exam study guide. Okay. Um, so I'm going to use my midterm study guide. All right. And I am going to have to add a little bit here. I am going to have to add the SciPy the SciPy.stats in. And I'm also going to try to remember the most important concept on the final exam. If p is less than alpha, reject the null. If p is less than alpha, we reject the null, and we have evidence for the alternative. We have evidence for a significant result there. Okay, so hopefully you can remember that, and I have that on my study guide. And we'll talk about this in just a moment. Let me transition into another discussion, okay? Where are you going to find your study guide? Okay, so do this. Open up anything in your data hub, and by the way, you can type in datahub.ung.edu and hit enter, and it'll come into your section of the data hub. Okay, once you're there, or you can click on any file on the course calendar. But once you're inside the data hub, go to File, Open. Okay, so File Open brings you into public material usually. And Regression. Okay, so this is where we started. Okay, and this is where the midterm study guides are. And this workspace is the place where I coached you on the midterm to go ahead and start. Okay, so try the workspace. That may be where your midterm study guide is, or if you save as, it'll be whatever you named it in here. Or another good place for it is, in fact, in public material. Okay, so try that. Try public material and lectures to find your study guide from the midterm. And the plan is to start from right there on our new pathway, right? So this is the end of my midterm study guide, and I'm starting my final exam study guide with hypothesis testing. Why am I doing that? Because the final exam is cumulative. So all of the stuff that I had from my midterm study guide is reasonable to have again on my final exam study guide. And I already created it and saved it, so there you go. And as you see, once again, if p is less than alpha, reject the null. Yes, that's the key thing in hypothesis testing. Okay, so with confidence intervals, I have on the PowerPoint, I have some slides about how to conduct it. But let's just suppose that researchers selected 50 students at random. They live in or around Dahlonega, but not on campus, right? And we're asking what their housing cost was. What's the rent they have to pay? And the idea is to estimate the average rent that a student has to pay per month. Okay? So what do? If we select 50 random students in this population, which isn't all of UNG Dahlonega, it's just those students who live near campus, right? What does it mean? Right? It means that when we repeatedly survey 50 such students, and we calculate the average of that sample of 50, that's called a resample, right? A resample of size 50, then the average rent will fall within the confidence interval 95% of the time. Okay, we're not saying that we're 95% confident that the population mean is in the interval. Again, it's what we're trying to estimate. Okay, so that idea is correct, but the fact of the matter is we're sure, we're pretty confident that about 95% of the time that we resample with size 50, take the sample average, that average will fall inside the confidence interval. Okay, so we do need to know how to interpret confidence intervals. I did point out that if you want some extra clarity for this, check out Notebook 14. It has a code block about halfway down, a little more than halfway down in that notebook, that shows us how to run a confidence interval. Okay, I have to calculate 4 things. I have to calculate the mean, I have to calculate the standard error, I have to calculate the degrees of freedom, and I have to put in the confidence level. Once I have that, this code will do it. And then the print statement is going to pretty everything up for us, okay? So you can take a look at notebook 14 for that, okay? And again, I just wanted to split these out. These are the 4 items we need to be able to run the stats.t interval, t.interval. And so this is the code that runs it. You're not going to be creating code on the final. It's like the midterm. It's multiple choice. So you should be aware of how this works and go ahead and make sure that in your confidence interval section in your study guide that you put in there what you need to know. Not just about how to interpret the intervals, but whatever you think is valuable about how to run them. Okay, and I tried to give you plenty of details here in the PowerPoint. Okay, so the next research question that's going to be helpful is one that uses an independent samples t-test. All right, and our question is, does perfectionism differ due to membership in an honor society? Okay, so I went ahead and set up the null and alternative hypothesis for you. Remember, there's almost always an equal sign in the null hypothesis, and then we specify some sort of difference, either not equal to or less than or greater than. But we've specified here not equal to. All right, so let's run that. Let's get into our t-tests, all right? So I've done the same thing here. And so we're using the personality data set, and it's called PERS. Okay, so honor, this is going to be all the students who are in an honor society. So we do pers.where, honor is a Y for yes. And we do the dot column for perf. Why? Well, remember that all of our hypothesis testing procedures, all of those functions use array data. So we're going to use dot column rather than dot select. Why? Because we need array data. And not in, those are the students who are not in an honor society. So we're going to compare them, or we're going to grab them with the dot where honor is equal to N for no. And again, dot column perf. Okay, so we're getting the perfectionism scores as arrays for the 2 groups. And then what are we doing? We're putting the 2 groups in the stats.ttest_ind. Okay, so the _ind, this is how we know that the t-test is an independent samples t-test. Remember that independent samples means that you cannot theoretically be in both samples, right? You're either in an honor society or you're not. You know, and those people who just got inducted, who said no when they answered the survey, but a week later the answer is yes. Okay, so theoretically you can't be in both groups, okay? So independent samples, and we run this, and we're looking at the p-value. The p-value is 0.717-ish, which is greater than 0.05. That's our standard alpha. So we fail to reject the null, and we have no evidence of any difference, right? So we can't reject this idea. Do we have evidence for it? Well, that's not the appropriate way to say it. The better way to say it is that we don't have any evidence of a difference in group means. Okay, we don't have evidence for this, is what we are allowed to say. All right. And I made the point again that we're creating arrays, and there is the code for you for the independent samples t-test. Okay, now we also learned about the match pairs t-test. If you recall, this was in the death penalty workbook where we were matching the states pre and post before the 1972 Supreme Court decision and after, okay? This one's going to be easier. We're looking at the personality data set, and stress 1 and stress 2 are the they're the same measure, but one was taken in the second week of the semester and the other was taken during the height of midterms. So we would think that maybe there was higher stress, right? That's why mu sub g equals 0. So I always use mu sub g for gain scores. Why? Because we always do post minus pre to see if students gained on whatever, because a lot of times we're measuring a training to see if the training developed benefits, right? If we're doing some training on how to shoot free throws, you know, you'd want your free throw percentage to go up after the training, all right? And the gain score measures post minus pre, so we get that gain that you make. And if the training had no effect, then the gain will be 0. You'll do just as well after as you did before because the training didn't help. But here we're looking for an increase, right? So that will explain the null and alternative hypothesis. Let's go ahead and run this. Okay, so our hypothesis, I set it up exactly the same way over here, except, oops, I didn't put greater than, I did not equal to. Sorry about that. The first thing I did was I created S1 for the variable stress 1, and that's just per stock column stress 1. We didn't specify any type of, males or females or cadets versus non-cadets. There's nothing else going on. We just want all the students measure on stress 1 and all the students measure on stress 2. We need both of them as arrays, so S1 and S2 are both using a per stock column. And I didn't run the first one, so the second one wouldn't work. Okay. And as before, we're looking at the p-value, and the p-value is less than 0.05. So the p-value is equal to approximately 0.0157, which is less than 0.05, our standard alpha. So we reject the null now. Okay, so now we're rejecting the null, and we have evidence for the alternative. Now, I will say that the alternative is actually that mu sub g is greater than 0, and we have evidence for that as well. Why? Well, because the t statistic is positive, and it always does S2 minus S1. And if S2 minus S1 is positive, right? If it's positive, then that means S2 was bigger. So there's more stress at midterms than there is at S1 and early in the semester. So we have evidence not just of not equal to, we have evidence that the average gain in stress was positive, right? Was greater than 0. Okay, so we have evidence that there's an increase in stress levels during midterms, believe it or not. Okay. So now we're going to take a look at some chi-squared tests. Okay, and there are 2 of them. One of them is called GOF, chi-squared goodness of fit, and that's we use to test a probability model. Okay, how would this be used? Well, it's used a lot in genetics, where we think we know, based on the genetics of the parents, what attributes the offspring will have. Okay, and we can test that with a goodness of fit. Test of independence compares 2 category variables to see if they're dependent upon one another. Okay, and for the GOF, we have the eye color experiment, and let me jump into that. Right, so I have data on the nationwide statistics on eye color, and what we do often is we take a class of students and I post, the 5 different definitions of what it means to have a certain color eye, and everybody places themselves in one of those 5 categories. And this is the example data from when we did this. And I forget, we had blue, green, hazel, and light brown and dark brown, I think. And I think I did those in order. So we had 5 students who had blue eyes, and 1 who had green, and 3 who had hazel, and 1 light brown, 2 dark brown, or 7 dark brown, or something like that. And then these are the percentages that the population have. Why did I multiply by 17? Well, because that's how many students I had in the sample. So we have to take the 17 and apply it to the percentages so that we predict the right number of students in each category. So this is the data we collected, 5, 3, 5, 1, 3, 1, and 7. And this is the data that's predicted by the probability model based on the nationwide statistics on eye color. Okay, and stats.chi-square, observed data, comma, predicted data, boom. And the p-value is large, specifically larger than alpha, so we fail to reject the null. And we have, oh wait, and I copy-pasted from before, so we have no evidence here that there's a difference Okay, so let me jump back. Do I have I didn't set up the, sorry. I did not set up the null and alternative hypothesis, so let me jump back in. So the null hypothesis for goodness of fit is that the data do in fact match the model, the probability model. Okay. And the alternative is that no, the data is different. Okay. So we have the same different, right? The null hypothesis is, yeah, the observed data is roughly the same as the probability model. And the alternative is, no, there's a difference. So we have no evidence for a difference. And I'm sorry about that. This is not stress levels. That was a copy paste error. Okay, so test of independence, chi-squared test of independence compares two category variables. So we do a dot pivot and compare where a student likes to sit in class to whether or not they're in an honor society. So the null hypothesis is that there's no dependence, right? So that where they like to sit in class and whether or not they're in an honor society are completely independent variables, independent. Okay? And the alternative hypothesis is no, there's a dependence. Where they like to sit, it depends on whether or not they're in an honor society. That's the alternative. Okay? And how do we run it? We have to make the matrix, right? And the way we do it is we enclose the top row in square brackets and the bottom row in square brackets, and then the full thing in square brackets. Why? Well, that makes np.array give us an actual matrix. And that's what this chi2 contingency is called. Why? Well, this is not only called a pivot table. Traditional statisticians also refer to it often as a contingency table. And so this is the chi2, chi-squared contingency. And I do that, and it spits out some stuff. And you have to know a little bit. This is the p-value. The p-value is 0.29, which is greater than alpha, so we fail to reject the null. And we have no evidence of a dependence. So in other words, we have not proven that where you like to sit in class depends on whether or not you're in an honor society. It turns out that whether or not you're in an honor society, those students in both groups still seem to have about the same preferences for front, middle, and back. Okay, we don't have any evidence that there's a dependence. Okay, in ANOVA, and you're probably getting used to this because of the project that you're doing. So remember that the null hypothesis is that all group means are equal, and the alternative hypothesis is that there is at least one mean that is significantly different than the others. And so what we're asking is there a difference in GPA due to where a student prefers to sit in class? So we're going to use the sit class variable and GPA. Let's check that out in the notebook. So ANOVA, remember, it's the mathematical extension of the t-test, the independent samples t-test, but the independent samples t-test can only compare up to two groups. So if I have 3 groups, 4 groups, 5 groups, more groups, I need to use ANOVA. Now, ANOVA needs array data. So you'll see that there's dot column on the end of all these 3. What am I doing? Personality variable where sit class is F for front, sit class where is M for middle, and sit class where we have a B for back, okay? So we're just simply making 3 arrays. We're getting GPA in array data for each of the 3 groups, and then we run stats F underscore one way. So if we have 8 groups, we just keep putting commas in group names. So we get an array for each of the 8 groups, and then we put the names of the groups in here, right? So we can use it for 3, 4, 5, however many we need, but we have to have an array data for each of those groups. And we do it, and notice that the p-value is just slightly less than 0.05. It's 0.0457, but that is less than our standard alpha, so we reject the null. What does that mean? It means we have evidence for the alternative. We have evidence that the average for one of these 3 groups is different than the others. Okay? This is why we often ran group stats when we were doing ANOVA. Why? Because we have evidence for a difference, but we have no clue what the difference is. So the group stats lets us ferret out, helps us ferret out exactly what the differences are. And it may give us reason to do an independent samples t-test to compare two groups and verify that there is in fact a difference there. And we did all of that when we went over ANOVA. So the last one is linear regression. So remember, we start with a scatter plot. We're going to compare these two numeric variables, optimism and thrill seeking. And also, we almost always use fit line equals true. We don't have to, but we almost always do, because when there is low to moderate correlation, like we have here, if there is any correlation, it's low. Why? Because the scatter plot dots, those data points, are just really scattered pretty randomly. And we can't really tell whether or not there's a trend. So we see a slight upward association here. And since we see a positive linear association, we do the linear regression. Again, we need array data. So we're doing dot column optimism and dot column thrill seeking for opt and thrill. And then we do stats.lin regress opt comma thrill. And they give us the line of best fit, the fit line statistics there, the slope and intercept for slope intercept form. They give us the correlation, which is positive and 0.3. So it's kind of a weak to moderate correlation. But look at the p-value. The p-value is a lot less than 0.05. Okay, so we are going to reject the null. And we have evidence of a significant, and let's also say positive, correlation between optimism and thrill seeking. Why? Well, because the fit line had a positive slope and the correlation between them is in fact positive. Okay, so we have evidence from the hypothesis test of a significant correlation, but we have evidence from the scatter plot and also from the correlation we calculated while doing the hypothesis test that the correlation is not only significant, it is also positive. All right, so those are the things that we want to add to our study guide. And then let me throw a couple more things at you, okay? I did mention group stats. You are seeing that on your project, so that could be on the final. Remember that we need array data for all of the SciPy functions that we use, the t-test, the chi-squared, the linear regression, the ANOVA. We've got to use arrays. All right. And this is the slide for linear regression. And you can pause this if you'd like to look more, but I did say all of these things. And I want to mention that there are some questions about scientific studies. So I wanted to throw some things at you, some extra questions that you can practice with. Okay. So according to a hypothesized genetic model, 25% of the pups born to a certain pair of dogs should have blue eyes. Test whether the genetic model is correct. What test would you use? Well, I hope you're going to say, hey, that's a chi-squared goodness of fit, and you'd be right. Chi-squared goodness of fit tests a probability model. It tests a genetic model. It tests a model for a game in Vegas, right? Like a game of roulette. They can test the equipment to make sure that the metal marble is actually landing an equal amount of the time in each of the squares or each of the slots. So yeah, chi-squared goodness of fit sees how well that observed data matches a probability model. Okay, what if we get a p-value of 0.82 when we run the chi-squared GOF? Well, we should fail to reject the null, right? We have no evidence that the observed data deviates from the probability model. Okay. Example 2, researchers are testing a new medicine for migraines, and they compare a treatment group to a control group. What is the correct test? Well, this is a little bit of a trick question because, yeah, it is a two-sample t-test. Now, remember, it's not a matched pairs t-test. That's for pre-test, post-test. and match data. What we have is a treatment group and a control group. So that is a 2-sample t-test. It's actually independent samples, right? So I'm going to throw that in. So it probably would have been easier if we had said independent samples t-test or matched pairs t-test. But yeah, it's a 2-sample t-test. It is not matched pairs. It is not matched pairs. Okay, and what if we get a p-value of 0.0168? What should we do? Well, we should reject the null because p is less than 0.05, which is our standard alpha. And what does that mean? If we reject the null, it means that the medicine works, right? The null hypothesis is that the average effectiveness in the treatment group is equal to the average effectiveness in the control group. And you're like, wait, shouldn't the actual medicine do better than the placebo, than the sugar pill? Well, of course it should. So the null hypothesis is that there's no difference, or in fact, we have no evidence the medicine works, right? The rejecting the null says, oh, the relief from the headaches experienced in the treatment group was greater than the amount of relief experienced by the control group. Well, that means the medicine works. Roughly speaking, we have evidence that the medicine works. Okay? And so, yes, we have one. In question 3, we have evidence suggests the medicine is in fact effective. Perfect. Okay, so one more, because there will be several of these on the final exam, and I'm trying to get you guys thinking in the right way. So researchers are comparing seating preferences in class to whether or not a student is in an honor society, which hypothesis should be run. Well, we just did it. And it's the chi-squared test of independence. We don't have a probability model here, right? We're testing 2 category variables to see if they're related. And if we have a p-value of 0.04, we should reject the null because it's less than 0.05, just slightly less than 0.05, but we should. And that means if we rejected a null, this is different than we found, but if we reject the null, we find that in fact, seating preferences depend upon membership in an honor society. That's what the result would be if the p-value were 0.04. Okay, so that's as good as I can do for a study guide and some additional study hints for the final exam. Remember, you will not be able to access this study guide electronically during the final exam, so make sure to print it out on hard copy. All right, good luck. Check with me on Teams if you have any questions. Good luck. I hope you do very well.